Hello, in this video I'm going to go through the whole of Physics AQA GCSE Unit 3, which is the particle model of matter. So without further ado, let's get started with today's video. The video starts off quite nicely because the topic is actually quite a nice topic, and I actually think it's not too difficult. And the first bit is just explaining the properties of the three different states of matter. And there are three states of matter, and their names are solids, which are shown over here, liquids, and gases. As you probably know, you can interconvert between these three states of matter by carrying out what's called state changes. Now, if you heat up a solid to its melting point, then it will eventually melt. And that's the first change of state, and it will go from a solid to a liquid. After this, you can keep heating your liquid up, and if all of it is evaporating, we call this boiling, but the change of state from a liquid to a gas is called evaporation. And you can go the other way as well. You can go from a gas back to a liquid, and that's called condensing. And going from a liquid back to a solid, this is called freezing. Now, in these three boxes, I've drawn out the particle arrangements for each of these three states of matter. Here you can see that in a solid, my particles are all in neat rows and columns, and they're all tightly packed together. In a liquid, I no longer have that regular arrangement of my particles, and they are still touching, but not in a regular arrangement, so there's a little bit of space between them. And finally, in a gas, my particles are no longer touching. So you need to be able to say how the particles are arranged in each state. So for a solid, I always use the word regular arrangement of particles. That just basically means that the particles are in rows and columns. In a liquid, the particles are in a random arrangement. They're no longer in rows and columns, but they are touching. And in a gas, they're in a random arrangement, and they're also not touching. Now, how does the particle diagrams relate to the properties of the three states of matter? Because in a solid, all of them are in rows and columns, and there's no space between the particles, these cannot be compressed. Same with a liquid as well, they can't be compressed. All of the particles are touching, they can't be forced close together. And then finally with a gas, because the particles are no longer touching, they can be compressed. You also need to know how in each state of matter the particles can move. So in a solid, the particles, we say, are in a fixed position. They can't move. They can vibrate on the spot if you heat them. In a liquid, the particles can move around. We say that these particles can slide past each other, and therefore they can take the shape of containers. So the particles can flow. And in a gas, the particles move randomly in all directions. Finally, what you need to know is you need to know how much energy each state of matter has. So if it's in a solid, this is the least amount of energy because the particles can't move. In a liquid, these have a bit more energy. And then finally, a gas, the particles have the most energy. And it's all because of the kinetic energy of them particles. they can move much more in a gas. How close the particles are together is a property known as density, and that's the next thing we're going to talk about in today's video. So if I look at these three states of matter that we talked about earlier, here I've got my solid, which is the most dense out of all three states of matter because the particles are closest together. Then I have, secondly, my liquid. And finally, I have my gas, which is the least dense out of all three states of matter. Now, as well as density being how closely packed the particles are together, you need to be able to define it in terms of equation as well. And density is also defined as the amount of mass in a given volume. So it's measured in kilograms per meters cubed. Now this can change. Sometimes it can be in grams per centimeters cubed. If you've not got a very big object, it's often measured in that. So to work out density, I will do mass in kilograms divided by the volume of the object in meters cubed. Now down here I've got a cube, and it's really easy to find out the density of regular shapes. For example, if I've got this cube and it has a side length of 2, remember that a cube, all sides would be the same, the width and the height. So that would also be 2, and that would be 2. And I'm just going to say meters just for the sake of this video to make it a bit easier. So to calculate the volume of that shape, all I would do is 2 times 2 times by 2. Now I have seen it where they've used other shapes, and you just need to know how to calculate the volume of regular shapes, and you should have learnt this in maths as well. So 2 times 2 times 2 gives me a volume of 8 meters cubed. And if that block then had a mass of 2 kilograms, I could work out its density by doing density equals the mass divided by the volume, 2 divided by 8, which of course gives me an answer of 0.25 kilograms per meters cubed. Now, if you were asked how you would carry this out experimentally, you'd need to say what equipment you'd use, and of course you would use an electronic balance to find the mass, and to find the sides of the cube, what you could either use is you could use a ruler, of course, or you could use what's called Vernier calipers, and these have a much higher resolution, so therefore you'd get a much more accurate value. And once you've got the length, width and height, just like I did, you could work out the volume by doing length times width times height. And to work out the density, then you would do the mass divided by the volume. As you're probably well aware though, not every single object is a regular object, and we still need to find the density of some irregular objects. And to do this, we use a principle called Archimedes' principle. So let's see how Archimedes' principle can help us find the density of irregular objects. So here I've got an acorn, and to find the density of this acorn, we're going to have to use Archimedes' principle. Archimedes' principle basically states that the volume of an object is equal to the amount of water that it displaces. It's said that in Greek mythology, when Archimedes found out this, that he ran through the streets of Greece naked, shouting "Eureka" when he found out that the volume of the object is equal to the volume of water displaced, because he was taking a bath and he noticed the water level rise when he got into the bath, and that's how he supposedly found this out. So let's have a look at how to actually do this then. So here I have a piece of equipment which is aptly named a Eureka can. And what I need to do is I first need to place my object inside my Eureka can, and we're going to measure the volume of water that spills over into a measuring cylinder. And remember to find the density. We're also going to have to find the object's mass. And remember to do this, we're going to use an electronic balance. After we found the mass, we're going to slowly add in the acorn or just any irregular object. And the reason why we're going to add it really slowly, you can use rope to add it slowly, and this is one way to avoid errors. We're going to slowly add the object. The reason is to avoid spills, obviously, into a full Eureka can. If any water is spilt, this is going to lead to random errors, and your volume that you calculate will be less. So therefore, you'll end up with a density that is a larger value. So I've slowly added the object into a full Eureka can, and the next thing I'm going to do is I'm going to measure the volume of water displaced. Using my Eureka can. Using my measuring cylinder. It's really important that you tell the examiner why you're doing this if they asked you for a method. So the next thing I'd say is my number 4 point would be that the volume of the object is equal to the volume of the water displaced. And then finally, I can find the density using density equals the mass divided by the volume. Now, other potential errors to look out for in this experiment is you could have a 0 error on your balance. This basically means when you turn your balance on that it's not reading 0. And you can always counteract 0 errors either by resetting your balance or by taking the number that's on the screen away from the value that you have. Also, I have seen things where it said about safety precautions with a practical like this, and remember when you're using water to always clean up any spills of water, as this can lead to slips and things like that, and make sure there's no electrical equipment nearby. This is just something that they sometimes like to ask. They sometimes ask about safety precautions in practicals where it's sometimes not easy to think about a safety precaution. What we're now going to look at is we're going to look at the energy changes that take place during state changes. So early in the video, we looked at the particle arrangements in solids, liquid and gases. So we're going to re-explore that, and we're going to look at the energy changes. So here I'm just going to draw a little bit of a heating curve. So imagine that I'm heating an object up and I'm plotting its temperature at certain intervals. So say, for example, every 1 minute or every 30 seconds, what I would notice is my temperature of my object would increase. And then when I get a state change, I start to get this flattening off in my graph. And we're going to talk about why that is in a second. But I would notice it when it goes from a solid to a liquid. And I would also notice when it goes from a liquid to a gas. And then it would start to increase at that same rate again. Now, we call the amount of energy needed to change state, we call that the latent heat. And this is just the energy needed to change state of 1 kilogram of material. And there are two latent heats here. We've got the latent heat of fusion, which is going from a solid to a liquid or a liquid back to a solid. And we have our specific latent heat of vaporization, which is the energy needed to change 1 kilogram of material from a liquid to a gas, or to go from a gas to a liquid. Now, what you're probably noticing is that the latent heat of vaporization is much larger than the latent heat of fusion. So obviously the reason why this is going flat is because energy is needed to change state, and we know that. But why is the vaporization much higher than the fusion. Well, just think back to them particle diagrams. When we're going from a liquid to a gaseous state, we are actually breaking the bonds between them particles. Just think, the particles go from touching to not touching at all and being able to move randomly in all directions. Now, we can actually quantifiably calculate how much energy is needed to change state for the latent heat of fusion or the latent heat of vaporization. And that formula is energy equals, which energy is obviously measured in joules, equals the mass, which is measured in kilograms, times by the latent heat of vaporization or fusion, which is measured in joules per kilogram. And remember that the latent heat of vaporization is always a lot larger because lots of energy is needed to break the bonds between the particles, and fusion is often a little bit smaller. And a lot of the time it asks for definitions of latent heat of vaporization or latent heat of fusion. If it was asking for latent heat of fusion, what you would say is the energy needed to change the state of 1 kilogram of material from a solid to a liquid. And for vaporization, you'd say energy needed to change state of 1 kilogram material from a liquid to a gas. So we just looked at a graph where we could use it to calculate the specific latent heat of an object, looking at the amount of energy needed to change state. But when we heat up an object, it doesn't always change state. So how do I calculate the energy needed to heat up that object without it changing state? And we call this property the specific heat capacity of an object. So the specific heat capacity is the amount of energy needed to raise 1 kilogram of material by 1 degree C. Now, how does this relate to the particles in an object? Well, if the particles are closer together and are a good conductor of heat, then that object's going to have a low specific heat capacity. So if it has a low specific heat capacity, it will heat up quickly. And basically, it just means that the particles are really close together. And because the particles are really close together, it's a good conductor of heat. If an object heats up slowly, then it's going to have a really high specific heat capacity. And therefore it would be a poor conductor of heat, and the particles would often be more spread out. Now, there is an equation to calculate the specific heat capacity of an object, and we're going to have a look at that now. So here I've got a question. It says calculate the specific heat capacity of aluminium if it requires 2.5 kilojoules of energy to heat up a 400 gram block from 30 to 45 degrees C. And the equation to calculate specific heat capacity, and I always tell my students to calculate it using a technique called FIFA. What I mean by FIFA is first you write out the formula. So if I write out the formula for this equation, it's energy equals the mass times by the specific heat capacity times by the change in temperature. So let's insert what I know then. So the energy is 2.5 kilojoules. So that goes into there. The mass is 400 grams times by the specific heat capacity times by the change in temperature, which is 15 degrees C. So the next stage after I've wrote out my formula and I've inserted my values is fine tuning. So there's things in this question which I need to change a little bit. For example, here it's been given to me in kilojoules, and also it's given me the mass in grams, and that will need to change to kilograms as well. So let's do that then. So it'll be 2,500 equals the mass, which is 0.4 kg, times by specific heat capacity, times by the change in temperature, which is 15 degrees C. So let's finally do my rearrangement, so I'll be able to do my calculation. So if it's times on this side of my equation, I'm going to have to divide it. So it'll be 2,500 joules divided by 0.4 kilograms times by 15 degrees C. And I put it in on the calculator exactly as I see it, and it gives me an answer of 416.6 recurring, and that's going to be measured therefore in joules per kilogram degrees C. Now, if it's 416.6, it'll probably ask me to give my answer to 3 significant figures, and this to 3 significant figures would just be 417 joules per kilogram degrees C. And I always underline my answer and I circle my unit just to show to the examiner that's my final answer. Something else they like to do is they like you to combine equations. So here it's a question where it says calculate the total amount of energy needed to heat a 400 gram ice cube from minus 20 degrees C to 5 degrees C and completely melt the ice cube. It gives me the specific latent heat of fusion and the specific heat capacity. So I'm going to need to combine the equations to get the total energy. So if I write out my formula, I'm going to do my FIFA again, insert my values, do any fine tuning, and then give my answer. So here, my formula here is going to be my energy equals my mass times by latent heat added to my mass times by my specific heat capacity times by my change in temperature. So let's insert my values again now. My energy will equal the mass, which is 400 grams, times by the latent heat, which is 334,000. And then I'm going to add that together with my mass, which is 400, times by the specific heat capacity, which is 4,200, times by the change in temperature. So going from minus 20 to 5, it's changing 25. Now the last bit in my fine tuning stage, not everything's in the right form. This is in grams and I need it to be in kilograms. So it's going to equal 0.4 times by 334,000 plus 0.4 times by 4,200 and then times by 25. And that gives me an answer of 158,800 joules. Now something that it might ask you to do here is it might say to put your answer in standard form to 3 significant figures, and to do that, that would be 1.59 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5 joules. Circle my unit, underline my answer. The last things we're going to look at is internal energy and gas pressure. So what is actual internal energy? And in an exam, they love to ask you to define this. And all internal energy is it's the sum of the potential energy of the particles and the kinetic energy of the particles. And because gases can move the most, they have the most kinetic energy, and therefore that they have the most internal energy. So let's have a look at the property that is pressure that gases can exert because of the fact that they have this so large internal energy. And pressure just basically is defined as the collision of gas particles with the walls of its container. Now, we can use internal energy to look at how to change the pressure inside it. One thing I could do to increase the pressure, there's 3 things that you could do to increase the pressure. And those 3 things that I could do to increase the pressure are, I could increase the temperature. And the reason why increasing the temperature would increase the pressure would be because the particles would have more kinetic energy, more internal energy, so therefore they'll have more collisions with the walls of the container, and them collisions will also be stronger. The next thing I can do, which also involves internal energy, is I could increase the number of particles there is. The more particles you have, the more internal energy there will be. And if there's more particles, there'll be more frequent collisions with the walls of the container. And then finally, the last thing has nothing to do with internal energy. The other thing I could do to increase the pressure is I could decrease the volume. And we'll focus on this one in a second. And the reason why decreasing the volume increases the pressure is because now they occupy less space, so therefore they will collide with the walls more frequently. So I said that we'd look at volume in a little bit more depth, and that's because of the fact that we can work out, if we know the pressure and the volume, we can work out, if I change the volume, the new pressure. And the reason is because pressure times by volume equals a constant at a certain temperature. So let's have a look at what that actually means in practice then. It says here that a gas occupies a volume of 0.5 meters cubed and a pressure of 150 pascals. Calculate the pressure if we change the volume to 0.15 meters cubed. And it says assume the temperature and the mass stays the same. So I'm not changing the number of particles and I'm not changing the temperature. Like I said, this equation only works if you keep the temperature and number of particles the same. So if we use that FIFA that we've seen already, this is my formula. And if I insert my values, my pressure and my volume originally is 150 pascals times by 0.5 meters cubed. And that will give me a constant. Now, I don't actually have to do any fine tuning in this, and it should be a pretty simple calculation. Just times in by 0.5 just halves it. So my constant is 75. So now if I go over here and I do the same, I can calculate my new pressure, because 75 is my constant and it equals the new volume, which is 0.15 times by my new pressure. Now this is just a simple rearrangement to get pressure now. It'll be 75 divided by 0.15, and that gives me an answer of 500. And remember, the unit for pressure is pascals. Now on the last slide, I said that the temperature needs to stay constant when you create your new volume to calculate your new pressure. But in reality, this is rarely the case, that the temperature will stay the same, because when you're doing work, when you compress a gas like's going on here, I've got a piston that I'm shutting, or a syringe that I'm shutting, and I'm decreasing the volume that they can occupy. And when I'm doing this, I'm putting work in. And when I do this, I'm making them particles move faster, which will increase the temperature. So if I decrease the volume, the pressure increases, and in reality, the temperature will also increase. And the reason for that temperature increase is because you're doing work. The work that you're doing to push them particles close together is causing them particles to move faster. Now, if I was to increase the volume, what would actually happen is the temperature should go down a little bit. And therefore, the pressure would decrease as well. And the reason why the temperature is decreasing is because now the particles are doing work. You had to do work to compress, and to expand back out, the particles had to do work. Now that's everything for today's video. Thank you for sticking along all the way to the end, and I wish you the best of luck in your exams.